Bijective functions. Hello everyone. To begin today's lesson, let's first look back at the foundation we have already built. In our previous sections, we explored two very specific types of mappings: one-one functions, which are also known as injective functions, and onto functions, which are referred to as surjective functions. Now we are introducing a new concept called the bijective function. Put simply, a function is classified as bijective if it possesses both of those properties, being both injective and surjective, simultaneously. As we move through the following slides, we will examine how this creates a perfect pairing between two sets and look at the specific conditions required to prove bijectivity. Introduction to bijective functions. Now that we have established the basic definition, let's dive deeper into what a bijective function actually represents. When we have a function f, mapping from set x to set y, and we determine that it is bijective, it creates what we call a perfect, one-to-one correspondence between the elements of the domain x and the codomain y. To understand this correspondence, think of it as a perfect pairing. First, it means that every single element in the domain x is paired with exactly one unique element in the codomain y. This ensures that no two different inputs lead to the same output. At the same time, the reverse is also true. Every element in the codomain y is paired with exactly one unique element in the domain x. This means there are no leftover elements in set y. Every single one of them has a partner in set x. In essence, bijectivity is the gold standard of mappings because it is a complete and unique pairing in both directions. In the next slide, we will examine the strict mathematical conditions you need to satisfy to prove that a function is indeed bijective. Conditions for bijectivity. Now that we have a general understanding of the concept of one-to-one correspondence, let's examine the formal requirements. For a function from set x to set y to be classified as bijective, it must satisfy two strict criteria. First, it must be injective, which is more commonly known as a one-one function. In plain English, this means that no two distinct elements in the domain x can share the same image in the codomain y mathematically. We verify this by stating that if the function of x1 equals the function of x2, then it must be that x1 equals x2. Essentially, every input must have its own unique output. Second, the function must be surjective, or an onto function. This means that every single element in the codomain y must be the image of at least one element from the domain x. In other words, there should be no leftover elements in set y mathematically. We say that for every element y in set y, there exists an element x in set x such that the function of x equals y. It is crucial to understand that these two conditions are mandatory. If a function fails to meet either the injective or the surjective requirement, it is not bijective. To help you visualize these formal definitions, we will now move on to a real-world example involving classroom seating in the next slide. Real-world example, the classroom seating. Now that we have covered the theoretical definitions of injective and surjective functions, let us move to slide 4 to understand bijectivity through a conceptual, real-world example. To help you visualize how these properties work together, let us consider a simple classroom scenario. Imagine we have a group of 10 students, which we will define as our domain x, and 10 chairs, which will serve as our codomain y. First, let us apply the first condition we discussed in the previous slides, injectivity, or the one-one property. If every student sits in a different chair, it means that no two students are sharing the same seat. In mathematical terms, each element in the domain is paired with a unique element in the codomain. Therefore, this specific mapping is injective. Next, we must check for the second condition, surjectivity, or the onto property. If every single chair in the room is occupied by a student, leaving no empty chairs remaining, then every element in our codomain is being used. This confirms that the mapping is surjective. In conclusion, because this scenario satisfies both conditions, every student has a unique chair and every chair is occupied, we have a perfect one-to-one correspondence. Thus, the mapping between the students and the chairs is bijective. Understanding this physical analogy will make it much easier for us to tackle the formal mathematical proofs and algebraic examples that we will see in the next section. Mathematical example. Now that we have explored the conceptual side of bijectivity using the classroom seating example, let us apply those principles to a concrete mathematical problem. Please look at the function f, which maps the set of real numbers to the set of real numbers, defined by the equation f of x equals 2x plus 3. Our objective here is to determine whether this specific function is bijective. To do this, we must follow the two-step verification process we discussed in the previous slides. First, we need to verify if the function is 1-1, also known as injective. As a reminder, a function is 1-1 if distinct inputs always produce distinct outputs. To prove this mathematically, we begin by assuming that the output for two different inputs is the same. That is, we assume f of x sub 1 equals f of x sub 2. Let's look at the algebra. By substituting our function, we set the equations equal. 2x sub 1 plus 3 equals 2x sub 2 plus 3. First, we subtract 3 from both sides of the equation, which leaves us with 2x sub 1 equals 2x sub 2. Then, by dividing both sides by 2, we arrive at x sub 1 equals x sub 2. Because we have shown that f of x sub 1 equals f of x sub 2 logically implies that x sub 1 must equal x sub 2, we can conclude that the function is indeed 1-1. Now we move to step 2, verifying if the function is onto or surjective. For a function to be onto, every single element in the codomain, which in this case is the set of all real numbers, must be the image of at least one element from the domain. To test this, we take an arbitrary element y from the codomain and see if we can find a corresponding x. We start by setting y equal to 2x plus 3. Now, we solve for x to find the preimage. Subtracting 3 from both sides gives us y minus 3 equals 2x. Dividing by 2, we find that x equals the quantity y minus 3, all divided by 2. Since we are working with the set of real numbers, any real number y, when subtracted by 3 and divided by 2, will still result in a real number. This confirms that every y in the codomain has a corresponding x in the domain. Therefore, the function is onto. Finally, we reach our conclusion. Because the function f of x equals 2x plus 3 has been proven to be both 1-1 and onto, it satisfies both necessary conditions. Thus, it is a bijective function. Pay close attention to these steps, because in the next slide, we will discuss some common mistakes students make when identifying bijective functions, particularly regarding the domain and codomain. Common mistakes. Now that we have walked through a successful example of a bijective function, it is important to address some of the common pitfalls. Many students encounter specific errors when trying to identify whether a function is bijective, so let's examine these carefully to ensure you avoid them. First, a very common mistake is assuming that if a function is 1-1, it must automatically be onto. This is not true. A function can be injective without being surjective. For example, consider a function mapping natural numbers to natural numbers, defined by f of x equals 2x. While this is 1-1 because every distinct input produces a distinct output, it is not onto. This is because the odd numbers in the codomain have no preimage. There is no natural number you can double to get 3 or 5, for instance. Because it fails the onto condition, it is not bijective. Second, you must be careful not to ignore the domain and the codomain. The bijectivity of a function is not just about the algebraic formula, but depends entirely on the sets x and y that we are using. For instance, take the expression f of x equals x squared. If the domain is the set of all real numbers, the function is not bijective because it is not 1-1. Both positive and negative versions of the same number result in the same square. However, if we restrict both the domain and the codomain to non-negative real numbers, meaning 0 and all positive numbers, the function becomes bijective. Finally, be careful not to confuse the range with the codomain. This is a subtle but crucial distinction. Always remember that for a function to be onto, and therefore eligible to be bijective, the range, which is the set of values the function actually hits, must be exactly equal to the codomain, which is the set of all possible values we defined at the start. Keeping these 3 points in mind will help you accurately verify bijectivity, which leads us perfectly into our final summary of the key takeaways. Key takeaways. Now that we have covered the definitions, worked through a practical example, and discussed common pitfalls, let us conclude with the key takeaways from this lesson. First, let's reinforce the core definition. A function is considered bijective if, and only if, it is both injective, which we refer to as one-one, and surjective, which we refer to as onto. This leads us to the concept of one-to-one correspondence. As we saw in our classroom seating analogy, bijectivity implies a perfect pairing between two sets. This means that every single element in the first set is matched with exactly one unique element in the second set, leaving no element left out and no element shared. Regarding the verification process, remember the steps we applied in our mathematical example. To formally prove that a function is bijective, you must independently prove both properties. For the injective property, you must demonstrate that if f of x1 equals f of x2, then it necessarily follows that x1 equals x2. For the surjective property, you must prove that the range of the function is exactly equal to the codomain. Finally, there is an important requirement to keep in mind. For a bijection to exist between two finite sets, x and y, they must possess the same number of elements, a property known in mathematics as having the same cardinality. If the number of elements differs, a perfect one-to-one correspondence is simply impossible.